Alright, great. This video is going to go through the one-star questions. There aren't too many for this one, but there are a couple scattered through the two-star questions, so you'll have to skip forward. Alright, question 14. Question 14 is an explaining type question. There's not a lot of working out I can show here. It's just saying white paper or the desktop, so the desktop down here, does not produce an image of an object. Does this mean the laws of reflection are not true for these surfaces? Explain. Well, this is getting into the difference between specular and diffuse reflection. So remember, specular reflection is when an object that is straight, or at least is very smooth at a sort of molecular level, all the light that hits at it is parallel coming down and is then leaving parallel. So let's just do a couple of images for that. So if we have a straight surface, everything comes in parallel to each other and leaves parallel. And because of that, we will see an image. Note, we're drawing these fairly far apart, but remember, there is a light hitting every single little micrometer here, in fact down to the nanometer, and then bouncing off in unison, and that's why we can see this image being created, or at least an image of some object over here. While for something that is a little bit rougher, like a desktop, then we start to see, well, we have in and bounce off that way, and then the next one might come in and bounce off that way. The next one might come in and bounce back that way. So it's not going to be all together. I mean, my desk here is just reasonably white, at least when I clean it. You can see some rough bumps in it, and we certainly see shadow, but we don't see any image in it. While at school we have that clearer coating on top of the desk that you guys sit at, and you can sort of see a faint outline of an image. It's not great detail, but it is faintly there. So realistically, this sort of description, you'd want to be coming down to the differences between specular and diffuse reflection. Okay, question 15. If you observe yourself in a plane mirror, what are the three significant optical facts about the image? So think about when we've been doing those labeling images in previous videos. We want to know, is it upright or is it inverted? Is it real or virtual? That is, can it be projected onto something? And is it a magnified or is it reduced? Or really, is it the same size sometimes? So let's think about it. They're virtual. Okay, a mirror image is behind the mirror. It is not, and yeah, we say it's sort of in front of the focal point, but there isn't a focal point for what's the word I'm looking for a flat plane mirror. The focal point is at infinity. So in some ways it's either positive infinity or negative infinity, regardless of which. If it's at positive infinity on the same side as us, then still our image and our object are in front of it, which means it's virtual. Or if it's on the back side of it, again, it'll be virtual. It is upright. And if I look in a mirror, I don't suddenly appear upside down. That would kind of be useless. And finally, it is same size. It is not magnified, and it is not reduced. You can also say laterally inverted. Okay, it's only asked for 3, but let's also put in laterally inverted. Okay, in that it is, we see things flip around the other way. Okay, 16. One method of taking your own photo is to photograph your image in a large mirror. If you're standing 2 meters in front of the mirror, what distance setting should you use to obtain a photo in focus? Would an autofocus camera focus correctly? Okay, so when we're taking a photo there, what we're trying to do is to take a picture of an image that is being created some distance behind the mirror. So let's draw it off there. We've got our person, we've got our mirror, we've got our image. Now, we're told that you are 2 meters from the mirror, which means that our image is also 2 meters behind. Okay. And we've got our camera. Let's draw a little camera there. and it's receiving light that is bouncing off from the mirror in all directions. Okay, so yep, while the light is really going from here and then going to here, to it looks like the light is coming from that far away. Okay, so it looks like the light is coming from 4 meters away, not 2 meters away. If you focused it on the 2 meters, you'd be taking a photo of the mirror, not the image within the mirror. Now, to a camera, it doesn't care. If you take a photo of something that's 4 meters away, or you take a photo of yourself 2 meters away from a mirror, to the camera, the light still travels the same distance. It is still the same distance away. Okay, so when it's talking about focal length, it's changing the type of lens within it in order to get a focal distance so that the focal point is 4 meters away from this object that you're looking for. So it either moves the lens backwards and forwards a little bit, or it might use a different size lens. I'm not a camera person, but you could ask a photographer. But in this case, well, we want f, well, I don't know what that was, we want lowercase f to be 4 meters, not 2 meters, because 2 meters would focus on the mirror, and an autofocus would probably focus it on the mirror itself, not the actual image that you're trying to find, because it's still seeing this object there, not to mention the wall would be around it. If there was nothing but mirror, then it would probably focus okay, but if it's got a wall or some other hard reference point to go off, it's probably going to autofocus poorly. Okay, question 17. If you wish to view your whole body in a mirror, what is the minimum length of such a mirror and where should it be placed? Okay, so again, let's go our person. Let's say that our person is 2 meters, because that makes the math easy. If we have a mirror that is, say, located here, let's make it really big. Well, if light hits here, it's going to go back to there. If light hits there, it'll go back to there, and so on. It won't get to our eyes till it hits the distance halfway between it and goes back. We saw that in class, and we can prove that because it has to be an isosceles triangle. Okay, this distance here will have to be the same as this distance here. This angle obviously going to be the same because of the law of reflection, and we're going to have a 90-degree down here, which means that these two triangles, being as they share a conjoined angle and a shared side and 2 equal sides, are going to be congruent, which means that these two have to be the same. So whatever distance up that goes is going to be the same distance up on the other side. We need to get to be that the distance A has to be equal to distance B, okay? And A plus B has to be from bottom to the head. So that means to the eyes. So that means that if we want to go from here to here, whatever that, what's the best way of thinking about it, has to be half the distance from your eyes to the ground. That's how high the mirror has to be up from the ground itself. Okay, so let's say that eye height equals 2 meters, then bottom of mirror and must equal 1 meter from the ground. Alright, so now we've got this situation where our person, and here is our mirror, but how tall does this mirror have to be? Okay, so obviously stuff up here doesn't have to matter, but from our eyes it has to be able to look here and hit the top of the head. Same idea as before. Okay, let's just make that a bit bigger because that was really tiny and he's going to suck. So, big head, eyes, and we have some mirror that's going up there and goes down there. Here is the top of that person's head. Do we need the mirror to go to the top of the head? No, we don't actually. We need the mirror to go to at least half the distance from his eye to the top of his head. Again, same reason, isosceles triangle, these two lengths are going to be equal, those two lengths will be equal, shared length, identical internal angles, which means that they're congruent, so therefore whatever that distance of the eye to the top, so from the eye to the top of the head, cut that in half, whatever that is, that's going to need to be our height. So the mirror doesn't have to go quite to the top of the head. It's easy enough to say, put it to the top of the head, make it half their height, but that's just going to be a little bit over the top. The real requirement is that the mirror starts halfway from ground to eye, and it ends halfway from eye to top of head. Okay, and again, it's all about isosceles triangles. Let's see. See, this question is actually giving a minimum length equals 80 centimeters. So the question is then, well, you would require an assumption that this person is, say, 160 centimeters, and that it is then started from the top of the head going down to roughly the midsection. That wouldn't work for someone of this person's height. If it was 2 meters, an 80 centimeter mirror is not going to see it. Remember, a mirror needs to be half the size of the object in order to see the whole object, or at least half the size of the object. Anything less won't work. 18. Explain the difference between a real and a virtual image. Okay, so you want to go back to your definitions in the textbook for this, but a real image is something that can be projected to screen. Okay, while a virtual cannot. So if we think about our curved mirrors that we've seen, or at least you may not have seen it by this point, but let's try to explain it without it then. So think about the projector in class. The projector in class is projecting an image forwards from the projector, a real image, and we're seeing it be focused on the screen. If it was a virtual image, then it wouldn't be projected onto the screen at all. We wouldn't be able to get it to go forwards. So projectors like movies or in the classroom, glasses are also examples of real images being created. A virtual image cannot be projected, and so we call it a virtual thing. You might be able to see it, but it's not something that can be put onto something else. Okay, that's the big difference. Again, double check your notes, and there's a lot of good description of this online. Sometimes a quick Google search of real versus virtual images might find you a way of describing this that helps you understand it. Okay, let's work through 19 and 20, and then we'll cut that video here for shortness, and that way I can upload more quicker. Oh, sorry, just 19. Okay, so in each of the following cases, state whether the light is parallel, converging, or diverging. Light from a light bulb. Okay, let's draw a light bulb. And it has some things there. So we've got our light, and that means the light is coming off all directions, straight lines, okay, which therefore means diverging. I'm just going to put D for diverging, P for parallel, C for converging. I'll make it easy myself. Light from a light bulb reflected from a mirror. So same as before, we're going to have our light bulb. Let's draw a circle. We have our mirror. Well, the light from here is coming off diverging, and so it will continue to diverge. That one might go flat, but these other two are diverging from this one that's perpendicular. This one here will continue to go out that way. This one here will continue to go that way. So again, it will be a diverging situation there. C, light from a star. A star is essentially a great big ball, so it's going in all directions, so it'll be diverging. D. Light from a star reflected from a concave mirror. Okay, so we're saying light from a star. Oh, hang on. The textbook's going parallel for C. Why? If you're at the star, then it's diverging because it's going in all directions if we think about it from the macro scale. But if you are sufficiently far from an object that might be putting out diverging light, the light is effectively parallel. And we say that limit is about a meter for small things, a few meters for big things. Like the sun, if you're more than 10 meters away, and obviously we are, the sun, if you're probably more than, say, 100 kilometers away from it, the light is probably going to be effectively parallel for your perspective. This is because if you think about this light, we've got all this light coming out here, but again, every single nanometer of that has a light ray going through it. Remember, light's pretty small, so by the time it hits us here on Earth, okay, that light is just coming down parallel. Okay, so you could explain it either way. The question is to explain where you're thinking about it from. I don't believe the textbook is really doing a good job of justifying why they've said parallel. Okay, D. So now we've got light from a star reflected from a concave mirror. Okay, so parallel light hitting a concave mirror, well, that means they're going to come back to the focal point. So they would be converging. E. Light from a star reflected from a plane mirror. Again, sufficiently far away that means they're parallel. They're going to hit a plane mirror, so therefore they will bounce back the same direction, which means that they would be parallel. Light from a star reflected from a convex mirror. Sufficiently far, meaning parallel. Hitting this, which means that now they're going to bounce off in all directions, so they'll be diverging. G. Light from a bulb placed at the focal point of a concave mirror. So let's draw our mirror. Let's draw our bulb. We'll make it small. So the bulb, we said before, is going to be diverging. Because the light is passing through the focal point, then that means it's going to hit and come back parallel. Alright, so check your images. So we've drawn light coming parallel, hitting it and coming back converging. The opposite must be true. If it's diverging from that point, then it will come back parallel. We call that the converse is also true. And finally, H. Light from a bulb placed at the focal point of a convex mirror. Well, it wouldn't work. Let's think about it. We've got our mirror. Now, if light's coming from this side, great, it'll bounce off. But our focal point is here. The light's going to shine onto the back, but it's a non-reflective surface. There's nothing to reflect. So it'd actually be none. All right. Let's do 23. It's not a mathematical question. And we'll finish with that one. Okay. Large diverging mirrors are used for security purposes in small shops. They are placed in the corners. What are the advantages of these mirrors for this purpose? So imagine essentially a large metal ball, and they've just cut out a small a corner of it and placed in the corner. So let's think about it. It's a big curved mirror. Let's try and do this. So it's kind of like a big curved mirror, and not only is it curved in 2 dimensions, it's also curved in 3 dimensions as well. Let's see if I can draw this. Something like that, and then you're going to have a mirror in all 3 dimensions. So light hitting here is going to go that way, and light coming from this way will probably go that way as well. So you could have it in multiple ways. But let's say that you're an observer over here. Okay? Maybe your shop, you've got some aisles and stuff, you can see down your aisles, but you can't see over into this far corner where someone might be shoplifting. So, but light from the person hits here, goes to the person. We can see light from here, might go up there and then come back, so you can see in between your aisles. If you're stuck at this corner position right near the door, you might not be able to see all these positions out here in your shop. So the big issue is that it allows to see, creates an image for the whole shop. It also makes it smaller, so it's easy to see more of it. You don't need to have a really big mirror there. You can have a small mirror up in the corner but still see sufficient amount. They are also, remember, it's a diverging mirror. And if you think about the ray diagrams we've seen so far, we haven't seen any ray diagrams where they end up being inverted, have we? They've all ended up being upright. Now, if you're looking at a security mirror and everybody looks to be upside down, it's kind of hard, and it makes it harder to judge that, oh yeah, you've definitely seen this. So they're giving you upright images, they're a little bit smaller, and they give a very wide field of view. So let's list those out. So upright, smaller, large, field of view. Okay, good things for security. Let's hit 25 quickly as well while we're at it. 25. Okay, so you're unable to see your reflection in a dull, unpolished car. However, if the car is polished, you can see your image. You've not changed the material structure of the car, so why does this occur? This is exactly the same as that first question when we talked about specular versus diffuse. Okay? Metal is very reflective. It has an electron layer in there, which you'll learn about later, but it reflects light very easily. But if it's dusty, if it's dirty, well, dirt is going to be, so dirt equals specular, sorry, not specular, diffuse reflection, therefore no image. Okay, shiny equals specular reflection, because that's what shiny means. If it's shiny, that means the light is reflecting as a fairly large amount towards your eye, and so it looks shiny to you, and so you can end up with specular reflection. That's all there is to this sort of question. 26. When you go for your driver's license, you're required to read an eye chart. Issuing centres use plane mirrors to make sure the correct distance between the chart and the observer is maintained. If a distance of 6 metres is required, describe characteristics of the physical setup of the chart and mirror, as well as the chart itself, to obtain this situation. Okay, so we need to have a distance DO plus DI equals 6 meters. Okay, so you might have, say, the chart above you, and you would be, say, sitting or standing below. You would need a mirror that goes from roughly where your eyes would be, and so they would need to put people of a fairly large mirror to account for people of different heights, because maybe the person's a bit smaller, a bit taller. We might need to be able to move that chart as well. So we would need a mirror. It wouldn't need to go all the way to the bottom, obviously, but we would need a mirror of some sort. This distance here would have to be 3 meters, and then that would have to be, so therefore that would be 3 meters as well. And so we would see our chart 6 meters away from us. If the room was bigger, maybe 4 meters, you would have to be 2 meters. So it would be any combination. 1 and 5 would also be fine. The mirror, so this bit here would have to pass through the bottom of the mirror to hit to the eye. Okay, so you have to be make sure that that mirror is low enough for each person. Obviously, there might be a minimum height to drive, I don't know, but we'd need that there. Let's see, the chart, don't forget the chart would be laterally reflected, so the chart would have to be mirrored. Okay, it'd have to be the other way around, wouldn't it? That way you can actually see the proper image when you're looking at it in a reflective surface. Let's see, anything else that looks like it'd be important? Now we've got something about the chart itself. We've got something about the mirror. It would have to cover a fairly wide amount. Wouldn't have to be that tall because we could see that. Okay, so probably wouldn't need as much up there that I've drawn there. Maybe more like, say, something like that. So it wouldn't have to be as tall, but the you would have the issues of maybe other people in varying heights, so that could be a bit of a thing. Now, question 27 feeds off the same thing, so we'll hit that as well while we're at it. It's asking us, why do some police cars and ambulances have the words on their fronts as shown in figure 17.24? Let's find where figure 17.24 even is. Right at the top of those questions there. And we can see, well, it's police and ambulance written backwards. Well, where are you going to see a police car and an ambulance? Coming from behind you, aren't you? You might see it coming from the other way, but if it's on the other side of the road, it's not super critical, but you need to be able to see the car behind you. So if it was written the right way, then it would be reflected in a mirror. Okay, but if it's written backwards, then in a mirror, if it looks like this, A-I-L-O-P, under a mirror, it would be P-O-L-I-C-E, which means then you can read it in your rear vision mirror. Alright, I think that's a good position to finish off. There are a couple more one-star questions. Yeah, a couple more other one-star questions, and we will do that in the next video. Thanks, guys.